In the previous video on Poynting's vector, we showed that the energy equation in differential form was minus d by dt of u is equal to div s plus E dot j. And in the previous video, we showed how the work done could be expressed explicitly in terms of the electric field and the magnetic field, and it turned out to be E dot epsilon 0 c squared curl of B minus epsilon 0 d by dt of E. So next we expand the bracket on the right hand side, giving epsilon 0 c squared E dot curl of B minus epsilon 0 E dot d by dt of E. So looking at the last term on the right hand side, we can re-express this as epsilon 0 over 2 d by dt of E dot E, and this term shows the time variation of energy inside the electric field. So we just rewrite our work equation as epsilon 0 c squared E dot curl of B minus epsilon 0 over 2 d by dt of E dot E. We need to change the term E dot curl B into a more useful expression, and in order to do this we have to use the product rule of differentiation. So we let G equals E and we let F equals curl of B. And for the sake of simplicity, we assume that the gradient operator for now is equal to d by dx. So the product rule is d by dx of f times g is equal to g d by dx of f plus f d by dx of g. So keeping in mind that we're looking for an expression for E dot curl of B, we rewrite the above equation as g d by dx of f is equal to d by dx of f times g minus f d by dx of g. So our above expression for E dot curl of B is equal to div B cross E plus B dot curl of E. So we now substitute the above identity into our previous equation of what the work was, and we have the work being epsilon 0 c squared div B cross E plus epsilon 0 c squared B dot curl of E minus epsilon 0 over 2 d by dt of E dot E. So if we look at the second term on the right hand side of the equation, we can see that there is a circulation inside the electric field. And we use Faraday's law in differential form, which relates the circulation in the electric field as a consequence of a time-varying magnetic field. Faraday's law explicitly states that the curl of E is equal to minus d by dt of B. So by using Faraday's law, we can re-express the work expression as epsilon 0 c squared div B cross E minus epsilon 0 c squared B dot d by dt of B minus epsilon 0 over 2 d by dt of E dot E. So the reason for using Faraday's law now, and in fact the reason for using the product rule of differentiation earlier, was so we could remove any circulation terms inside the electric and magnetic fields, and we could re-express them in more convenient forms. So we want to express the second term on the right hand side of the equation, which concerns itself with the time-varying magnetic field, in a similar manner as how we express the time-varying electric field energy. So when we do this, we find that that second term is equal to epsilon 0 c squared over 2 d by dt of B dot B, and the final term doesn't change. So the last step is to factorize the right hand side of the equation by the time-varying quantities. When we do this, we find that the work E dot j is equal to div epsilon 0 c squared B cross E minus d by dt of epsilon 0 c squared over 2 B dot B plus epsilon 0 E dot E. So if you recall from the first video, we derived the energy equation as minus du by dt is equal to div s plus E dot j. And looking at the above equation, we can show that the energy inside the electromagnetic field contains both a magnetic field and an electric field. And the energy U is equal to epsilon 0 c squared over 2 B dot B plus epsilon 0 over 2 E dot E. And when you take the highlighted term in yellow over to the left-hand side of the equation, you can show that Poynting's vector S is equal to epsilon 0 c squared B cross B, using the fact that A cross B is equal to minus B cross A. So, over the course of these two videos, we have successfully derived Poynting's vector for the energy flow inside electromagnetic fields.